Hello, this is Spencer Sheen coming to you with another live coding tutorial. The subject for today's video will be Vermont, the state of Vermont. So I'll be creating a 3D population density map of the state of Vermont. And my intention today is to follow my usual workflow for creating these maps. Now I have a pretty strong foundation in how I create these maps, so you'll see I have a lot of code already written that I'm going to borrow from, and you'll see my workflow is pretty stable at this point, but I'll explain what I'm doing as I'm going through, and hopefully it'll give you a good idea of how I create these maps and how you could pull from my workflow to assist you if you are interested in making such maps. If you would like to follow my workflow, it'll probably be easy if you go to my repository, raster portraits, and you could download this repository. You could fork it or just download it, whatever you want to do. And then once you've done that, you'll have access to some of the functions I've written that make things a little easier. But first things first, I'm going to start with one of these functions. And you can see here I have used the new portrait function to start working on a new portrait. Now this is a function that I've written, and I believe it's in the... So in my R profile, I have this created. And so every time I open this repository, it'll run this code. And so it's sourcing this file, which I have in R utils onload.r. And so if we go there, R utils onload.r, we can see that I have this function defined, the dot new portrait. And the reason I put a dot in front is so that it's not showing up in the environment. Any function that has a dot to begin it, a period to begin the function name, it won't be showing up in your environment here. So that's just a way to keep your environment less cluttered. So what this function does is it's just taking templates that I've already created. And these are script templates. There are scripts. And if it's an elevation map that I'm looking to make, then it'll take the elevation script. Or if it's a population density map, I can specify population and it'll take that script. And I have those templates here in the template folder. And you could see there's the elevation subfolder or population subfolder. And there are two scripts. There's the render graphic script and the markup script. So render graphic will be where we're actually creating the 3D object and using raster to create a high quality render of that object. The markup script will be where we're adding the annotations. So I'm not going to go too much deeper into that, but just that's a little background on what this function is doing. So I'm going to go ahead and use it now. So the first argument I pass is the name of the map, and this will primarily be used to create a subfolder that will hold the code for this this graphic, this map. And so that's the name here, will be Vermont, and then I specify that it's population density, just with population. And of course, I spelled it wrong. Vermont population. Okay, and so now you can see the map object is assigned to Vermont here. And there are a few places where the new portrait function is just replacing certain keywords with Vermont throughout here. Yeah. So we have the whole script here already. And now you could run this whole script as it is and it would create a map, but there are a lot of default settings that I have on here, like the color palette and the Z scale and the angles and the lighting that I'm probably going to want to play with. And so that's really what I'm going to focus on here. I have the skeleton of code set up, but I'm just going to go through. I'll change the color palette. I might change the Z scale so that it's not as exaggerated, or so that it's more exaggerated. I might rotate the object, rotate the scene, and then finally in the high quality render, I might play with the lighting, and I might create a reflective surface. So that's what I'm going to be working through here. But first things first, we have all the packages loaded. So now I have Vermont assigned to the map variable, and I've already downloaded the population data. If you've followed my work or the other YouTube tutorials that I have, you'll know that I'm using the contour population data. I've downloaded the data for the United States, and I have it in my data folder here. You can see the path. But instead of reading that whole data set into memory, it's a pretty large data set, so I don't really want to do that, especially when I'm working with just Vermont. Vermont's a pretty small state. It's going to be a lot better to just read in that data as opposed to reading in the entire United States. So what we're able to do with a geopackage file is we can access some of the metadata, and then we can structure a query that will return only a portion of that data. So if you're familiar with SQL, this is along the lines of that. So we'll effectively be creating a SQL query, but R makes it really easy to do that, specifically the SF package in R. I feel like I didn't explain that very well, but we will just work through it. So D layers here is, this object is returning the layers of the data. So if we look at D layers, we see there's one layer, the population. And then DCRS is pulling the CRS, the coordinate reference system, from that data. Sorry, I'm also having to remember specifically what all of this does. So DCRS, so that's the defined CRS. And so we'll be able to use that to make sure the data projection is correct and that our other data that we're going to read in is correct. For instance, we need to limit the population data to the state of Vermont, the state that we are looking to focus on. So I read in the Vermont data with the states package, or the states function from the Tigris package. And I know a lot of people have pointed out that the Tigris package only works for the US, which is true, but I would encourage you, I'm sure there are other sources of administrative boundaries for whatever region you're in, whatever country you're looking to do. So you just need to do a little Googling and searching around to find that. But I will use the states package, and then I'm transforming the data so that the CRS matches the CRS of the geo package there. And then finally, we want to filter the states data. You can see there's 56 observations, so that's 56 states and territories of the United States. But we only want Vermont, so let's go ahead and filter it for Vermont. And there, you see we only have one observation now. And the final step we need to take before we actually read in the contour data is to create this WKT filter. There's an argument name on the stRead function from the SF package, and the argument name is WKT filter, and essentially it's creating a geographic filter that you can apply to the geographic data, so that you're only pulling in data that falls within that bounding box defined here. But it has to be in a specific text format, so we can use st as text, as we see here, on the st object that we already created, and specifically on the geometry variable of that object. So if we do that, then you can see, well, let's just take a look at what this object is. So it's a defined polygon essentially, but it's a text. This is a character variable. And if we scroll up, we can see that it's defined as a multi-polygon. But this is still just a character object. Okay, so next we read in the data. And see, that was pretty fast. And if we plot the data, we'll see what data was returned by this filter we applied. All right. Like I said, this filter creates a bounding box, and it only returns data that falls within that bounding box. So that's what we're seeing here. This is the bounding box of the state of Vermont. So Vermont itself will be enclosed in here. So the last thing we have to do is a join. So we'll use the stJoin function from the SF package. And if we structure the function like this, then it will return all of the contour data that falls within the ST boundaries, which again, the ST boundaries are the state of Vermont. And I can illustrate this a little better if we say, so if we do that, then we'll see the state boundaries are also showing up here. So these are the boundaries of the state of Vermont. And when we do this stJoin function, it will only return, if we set left equals false, this argument, then the join will be an inner join. So it's only returning values where they are matching on both the left and the right side. So the left side being the data object that is all of the data plotted here, all of these hexagons, and the right side being the Vermont boundaries. So essentially, it will return all of the hexagons within the boundaries and all of the hexagons that touch the boundaries. So if we do that, so we'll usually take a minute to do the join, but not too long. And then let's plot that join. Let's plot that data and see what it looks like. And there we go. So now we've limited the contour data to only show those hexagons that are within the boundaries. These next few lines of code are setting up, this is set up so that we'll be able to create a matrix of the data. Right now, our data is essentially it's in a data frame format. It's an SF object. So if we were to look at this st underscore d object, we have a data frame where one variable, one column, is the geom column that has the polygons defined. So each row here would be a hexagon, an individual hexagon that's plotted. But for ray shader, we will need to transform that into a matrix format, because that's the easiest way to work with it. And so when we're transforming it to a matrix, we'll want to know the exact dimensions that we want to define. So that's what we're doing here. We're setting up the bounding box of the state, which again is Vermont, and then we're calculating essentially the width and the height of that bounding box and defining that aspect ratio. So if we do that, then we define the x rat, the x ratio, and the y rat, or the y ratio. And we can see the way that I have this set up is whichever one is longer will be 1, and then the other one will be will be less than 1, some number between 0 and 1. And you can see here that number is 0.621. And now that we have that aspect ratio defined, we will define the size of our matrix. And to start out, since I'm going to be working through this and trying to render quickly and see what kind of color palette I like, I'm going to start with a small size. And so I usually go with 1,000. And then I'm going to use this function to create a raster object of the data. This is really just an intermediary function, because I then need to convert it to a matrix, but I'm not sure. I haven't figured out a good way to take the data from its SF form that we have it here to a matrix form without first using a function like this. So if anyone knows a better way to do that, please reach out to me. I'd love to eliminate this step. But what's happening here is I am defining the x width, or the number of cells in the x direction and the number of cells in the y direction. So this is where the aspect ratio is coming into play. So if we do that, and then finally we will define our matrix based on that raster, and again defining the number of rows and the number of columns based on the aspect ratio. There we go. We have a large matrix that's 5 megabytes in size. So again, I'm just going to work through this quickly and play with different color palettes and different lighting schemes. And then when I finally find something I'm going to settle on, then I'm going to increase this probably to 8,000 or 9,000. And we'll see that the size of this matrix will then be between 400 and 500 megabytes. And I found from my computer that's really the upper limit, but it creates really it creates high quality graphics, so it works for me. If you're on a machine that has more memory limitations, you might need to not go quite as high as I go here. Or if you have a better machine, you could kick it up a notch. All right, I have a predefined color palette here. So I'll just go ahead and render that to begin with, just to show you what this is doing. All right, so there is an initial render using this predefined color scheme and predefined camera rotation. First thing I notice is that these heights are really exaggerated. I personally do not like when there is such an exaggeration of the height, because it creates a very spiky feel to the maps, which to me, this sounds weird to say, but it seems hyper unrealistic to me. I like these to be the height exaggeration to be more subtle, so that it looks more natural. It looks like something that could exist on a table or a plane, for instance. And so you can adjust that by moving this value up. So the higher you make the Z value here, the less these heights are going to be exaggerated. So if we run it again, there, see I set it at 75, and now you can see these heights are much more subtle. They might be a little too subtle for our purposes. Let's see what 50 looks like. And keep in mind that every time I do this, I am closing the window. Oh, this says use close 3D instead. So I close the window, then I re-render it. Otherwise, you'd just be plotting on top and on top, and it just doesn't work. There, all right, 50, that looks a little better. You have some notable height over here. Oh, this is kind of making me dizzy. Okay. I'll just render the camera again so that it's back where I left it. Now I have a few setup lines of code here where for every graphic like this I create a subfolder within my images folder to hold all the graphics related to this. So I'll go ahead and do that. I'm pretty sure the images folder I don't track on GitHub either, because it is just massive with all of these renders in there. So I keep those large files off of my Git tracking. So just keep that in mind if you do go ahead and copy that repository. Now I'm defining the out file for the high quality render. Then I create this. This is sort of a metadata object that I'll use when I'm marking up the render. So more on that later. Now, since I'm still in my figuring it out mode, so I'm still testing the color palettes and the lighting. And so when I do this, I want to change a few things so this will render really quickly and I can just get a snapshot of what it's going to look like. So one thing I do is I turn samples down to 300. I turn preview on, and I make the size of the render smaller. So I'm setting it to 800, 800 here. And so now once I render that, it should be popping up here pretty soon, and I'll be able to preview the render as it's happening. There we go. So you can see the render. Now this is a default color scheme, but my idea that I want to try to bring to life here for Vermont is I want to use something that's kind of a fall color scheme. Since Vermont is so well known for maple syrup and leaves changing, I'm thinking some sort of brown orange, kind of earthy color palette like that. So one thing I do when I'm trying to pick a new color palette is I can just scroll through some of these other maps I've done. Because if I see a color palette that's even close, then I can just steal it since I've already defined it, and I can go from there. Louisiana color palette is that's kind of what I was thinking. So if I look at the render graphic, golden brown. Okay, I'm gonna try this one. So if I just copy all of that, here I'm gonna replace my color palette. Oops. So this is using the National Parks palette package. So I need to load the package, and then let's try again. Okay. I'm intrigued. Okay, the only thing I want to try is switching the order. So if I say swatchpot colors, it'll show me, this shows me the order of the colors in the palette. So we see we're going from light purple up to dark purple, and then dark orange down to light orange. But instead of that, let's rearrange that order and say, so colors 4 to 1, and then 5 to, and then 10 to 5. So I'm going to put the darker colors on the outside and the lighter colors on the inside. Oh, there we go. There wasn't a 10th color. If we look at the colors object here, it only has a length of 9. That's what was happening. Okay, so let's call it CF, just so I don't get confused. Okay, and then CF. There. Now the reason I do that is so that if we go back to this object, the way that these end up in practice, you have a lot of low density areas, and then you have these areas with peaks where there's data just shooting out. And when we light the scene, we'll have rays of light will be coming in and hitting these objects. And right now I have the lightest areas on the end of on the tails of the data distribution. So at the lowest end and at the highest end. So in other words, the lightest colors are assigned to these values that are not having the most light hitting them. Instead, if we have the transition, if we capture it so that the transition between the really flat hexagons to where they're really starting to pop up, if those are lighter areas, then the light will really reflect off of them. And hopefully I can show you now and it'll make a little more sense. Okay, yeah. So here you can see like this area, all these little bumps where there's enough population density that it's starting to pop up out of the flat area. The light is gonna is going to reflect off of that pretty nicely, I think. So let's see. Let's just give it a shot and see what happens. Yeah. So you can see these areas are, I really like that. If anything, the one thing I'm not liking about this color palette is how dark this piece is. How dark the lower ends are. I'm not sure if that's a deal breaker for me right now. I also don't love that angle. So let's play with the angle here. So that's a 0 degree angle. So the scene isn't rotated like that with 0 degrees, but a 45 degree angle means that the scene is tilted like that. And the reason I do a 45 degree tilt is so that the height of these really shows up well in the final render. Let's try 10. Sometimes when you're playing with this, instead of going from like 0 to 10 to 20, it can be helpful to just jump up to like 45, so that you can define the extremes, and it's much quicker to see if you're going in the right direction or if you want to go the other direction. It helps you define the boundaries that you want to set for yourself. I just don't know. So one thing I do like about the population center here is that if we are, oh man, there must have been an update to X quartz, because I do not remember it used to be centered along an axis. So this, for instance, was not possible. But now this seems possible, which is kind of funny. I wonder what that'll look like. Let's just go ahead and render that. There must have been an update to the RGL package, and that's why I'm getting these other errors. Oh yeah, that's not what I want. So let's just go back to what we were doing. So since this highest population density is over here, I do want to make sure we sometimes it works best when that is towards the back of the image so that the shadows are being cast behind it. So that's what I'm going to go for here. I'm also aware that I'm starting to, it's never a good idea to rotate your scene too much because you don't want to disorient the viewers of your graphic too badly. All right, so let's try that. And then colors. Okay. I like how the light is hitting off of this, hitting off of all of these areas. I'm still thinking that this is too dark in the lowest population density areas, so I'm going to come back up here. And one way so there I just took off the darkest purple. And I also lessen the bias so that it shifts this way a little bit. So I think that will, in practice, move the lightness up these bars a little bit. And that does look like what happened. So I'm pretty happy with that. The last thing I want to try, though, is adding a reflective surface. Nothing too reflective, but I'll show you here in a minute what I'm talking about. First, we're about to see this. Okay. So if I go back to Ray Shader Portraits, you can see I use this as reference pretty often. Here, Massachusetts is one example. You can see that the surface is actually a microfacet surface. There's subtle reflections coming off of it, which just adds a really subtle element. Same with Hawaii. Hawaii, it's a little more reflective, so you can see that. So I want to add something similar to this Massachusetts. So I'm going to come in here and look at what I did. And it's this, this argument of the render high quality function that will determine it. So it's defining the ground material. So the ground material will be everything here that's white that's not data. So it's what the data will be projected onto. And I'm using the ray render microfacet function. And without getting too in depth, I'm just going to explain the arguments I have here. The roughness function will define how reflective the ground is. So a roughness of 4 is giving us the reflective, it's giving us this level of reflectivity. So it's pretty subtle. If we were to go down, if we were to make it like a 0.1 or approaching 0, then it would get very reflective. The eta argument is setting the this is the this is the reflectivity of the surface. Let's just look at the help file to be sure. So you see we have eta and kappa here. Okay, so the refractivity of the material. And then kappa is the absorption of the material. So I don't know if I'm taking the best approach here, but my approach has been to essentially just play with it. I haven't found a ton of documentation on how to actually set these with with real purpose. So I'm just adjusting them until I get a combination that works well. And so the refractivity will affect what is reflected at you, and the absorption will be what's not reflected. At least that's how I'm thinking about it. So I kind of set these I tend to set these just in opposite directions. And you can try just not having kappa at all, or perhaps just using eta, but I'm just going to follow what I've been doing because it's been working for me. So let's see. I would like this to be a bit of a brown color, with maybe a little red reflectivity. So that's what I'm going to go for. And so there are 3 arguments, and the 3 arguments are the red, green, and blue areas of the spectrum. And so, for instance, as I understand this, for the refractivity, if you set R the highest, then you're going to get a higher reflection of red. If you set R the lowest, then you're going to get a lower reflection of red. And as you adjust these in combination with each other, you can get different value or different effects on the overall graphic. What colors are being reflected, what the surface looks like, those sorts of things. So to make it brown, if I want to make it brown, then I think I would want red and, would that be red and blue? I don't know. So if I say like 0.75, 0.1, 0.75, and I'm just going to take kappa off for now while I'm playing with this. Let's try that. That is pretty green. That is green. Okay, so why was that green? Because I did red, green, blue. Okay, I think I've settled on this. So what I like here is the way that this color palette is working together. This purplish color is actually coming through. More is brown, which was the intention. So it looks as if it's going from a coppery brown to lighter gold and then up to orange at the highest population density. The one effect I didn't achieve very well, which is coming through a little bit, you can see with the shading here, this red reflective, the red reflection in the material. Here, let's try, if we lower the roughness level, it'll make it a little shinier, but when we do that, the background gets darker because none of the light is being absorbed there. Yeah, see, I feel like that's a bit too dark. We do have the reflections coming through a little bit, so that's pretty neat. But I do think the contrast isn't great enough there, so I'm going to increase it still. I think I'm going to settle on 4. If I set the roughness to 4, then there will just be a very, very subtle reflection showing up in the surface. And another thing about the reflection is it really shows up better when there are high population areas around the edges, because so this population area, this would have a good reflection here, except it's covered by the data because there's population around it. And these ones along the edge are, they're just not that substantive to create a reflection. Now, I still want to increase it a little bit. And so when I say the contrast, I mean the contrast between this surface and the data here. So the contrast between the two, like, it's pretty hard to see the difference. And I want that, it doesn't have to jump out at you like you would want it to with text, for instance. Like, you want text to have a very high contrast against the background so it's easy to read. But for this, you just, it doesn't need to be that high of contrast, but I like this contrast better, I think. Then the only other thing I want to play with is I think I might have it rotated too far. So I'm going to try it without that rotation, or with a slightly muted rotation, 20 degrees instead of 30 degrees, so that it's oriented more naturally. If I had set it to 0 degrees, then that would be just a straight north-south orientation that people are used to. And I think your default reasoning should be keep the north-south orientation as much as you can. If you're going to rotate it more, you should have a good reason to do so. I don't think I have a good reason to do so, so that's why I'm lessening it to 20 degrees. Yeah, I think that's good. All right, so I'm happy with this. I think it's different from what I've done in the past. So I'm going to go ahead and set up a final render. So when I'm ready to do the final high quality render, this is the one that's going to take a long time. So there are a few things I need to go back and change. The first of which is the size of the matrix. I need to, since the matrix is the initial data that goes into creating the 3D object, we need that data to be high resolution as well. And we can do that by increasing the size of the matrix. And so, like I said, I try to shoot for a matrix that's between 400 and 500 megabytes because I try to maximize the resolution. Ooh, can I go to 10,000 with this one? It's probably going to be too much. No. All right, so I'm going to try this one at 10,000. That's about the limit for any of these that I do. But you can see it's just under 500 megabytes. So we should be fine. And the other thing to be aware of is you need to adjust your Z scale. Since you've increased the resolution of the data, that affects, this Z scale is essentially a ratio between how high the data goes based on how wide the data is, or how many the units of measure across the X and Y axis. So essentially, since we've increased the resolution by tenfold, I'm going to do the same thing here by dividing the Z by the resolution that we've set. Okay, so this is going to take a while now that the resolution is so high. Okay, that took a little while, but now we have the object rendered in the window. And we're just going to work through these other setup functions. So there we have the angle defined. You can work through these. You don't need to run those, actually. That's just a habit of mine. Now, the last thing we need to do before we run this script, this render high quality function, is adjust it back to where we had it. So we need to turn the samples up to 450 because that is going to increase our resolution. Turn preview to false because I find that sometimes the render will fail if I have preview turned on. I assume that's because of memory reasons. If you have the preview on, it's just going to take more memory. And then finally, we're going to increase our width and height. And I typically will set these to the same dimensions as the matrix, so that basically one cell ends up being 1 pixel. And with that, we're ready to render. So we're off. Now, this is a really large render for me. I imagine it's going to take, over 2 hours, potentially over 3 hours. So we'll see. I'm going to let this run. The last thing I like to do while it's running, I'm on a Mac, and on Mac, there is a command called caffeinate. And when you run caffeinate, it will keep your computer running so that it won't go idle. So I always do that when I have these large renders running, and I can just leave my computer and not worry about it. If that doesn't happen, I've had it where my computer does go idle, and it will just pause the render. It doesn't run the render, it just pauses it. So that's not the worst thing in the world, but it does suck if you just left it for, a couple hours and you come back and realize it paused after 30 minutes or whatever. So it's running now, and I'll be back when it's done. So there we go. Looks pretty much as expected, for me at least. And you can see as I zoom in, the resolution is pretty good. So I'm pretty happy with this. Now, all that's left to do is to add the final annotations, and I'll add those final annotations in my next video. So make sure you're subscribed to my channel. Otherwise, that brings us to the end of this video. Thanks for making it this far, and leave a comment below, or feel free to reach out if you have any questions. You can send me an email and I'll respond as best I can. Thanks.